first day. So we've looked at all the planets, right? But what about poor old Pluto? Well, Pluto is not a planet anymore. Not according to some astronomical groups. To some people it is, some people it's not. When they discovered Pluto, it didn't take long to realise that it too must be, like Ceres, quite small. Because it was so dim. Now compared to the Earth, that's the size of Pluto. Much, much smaller than the Moon, you can see, considerably smaller. And they've just recently discovered that Pluto has 4 moons. As you can see, just back in July of this year. Up until then it had 3. The first one they found was Charon. And compared to the planet, the Moon is very, very close in size. In actual fact, Pluto has the largest moon of all the planets and dwarf planets and anything that we know of so far. By a long shot, as you can see. It's not that much different in size. In fact, the sizes are so close that rather than the Moon going around Pluto, they actually orbit one another because the centre of gravity is somewhere between the two out here. So they both orbit. I can't do that very easily, but they both orbit that centre of gravity. You might want to know if that's the object with the biggest moon for its size, what the next one is. That's the good old Earth. We have the second biggest moon for our size. Because our planet is much, much bigger, our moon has to be bigger, but ours is the second in line. Now, if Pluto wasn't a planet, if everything that was called a dwarf planet had to be called a planet, what would the result be? Well, we've got our 8 planets there, but if for some reason we decided anything that we call a dwarf planet now would be called a planet, then we would get something like this. We would have Ceres in the middle, all the usual ones, Pluto, and then 3 more, Haumea, Makemake, and Eris. They're also dwarf planets. So perhaps, maybe we might have to call those planets as well if we didn't kick Pluto out, because they're all similar orbits, 13 in total. You'd have to remember those. But there's more. There are other objects that they think when they find more information may actually be dwarf planets as well. They may fit the definition. And so some more might have to be added. So there's Quaoar, Orcus, this really great one, 2007 OR10, and Sedna. So there could be a few more if we were to loosen up the definition. There could be 17. But they theorise there's possibly another 50. So there could be maybe 67 if we didn't kick Pluto out. So maybe it's a good thing, don't know. So we've got all these planets. How are they formed? How do these planets actually form around the star? The planets form in these clouds of gas, and you can see a lot of them in telescopes. The Orion Nebula, which is becoming visible now as we get towards Christmas, the Orion Nebula, which is sort of where the handle joins onto what we call the source beam. That little fuzzy bit in the corner is the Orion Nebula, and if you come along here to one of the viewing nights, I'm sure someone will point it out. It'll be one of the favourite objects, most definitely. You'll probably find most of the telescopes will be on. And these huge gas clouds, masses of gas and dust and all this material in there, trillions of kilometres across, enough to make billions of Earths, masses of material. And all this gravity slowly brings this material together. Like when you pull a plug out, all the water rushes to the hole in the middle. So that's like gravity pulling all this material into the centre. But you'll see that further out there might be little eddies as well that start swirling. And that's how they think the planets are formed, that this material is being brought in and these eddies start swirling around in this material, and that starts to coalesce and start to form planets and asteroids and other things as well. But if I point the Hubble telescope, this is actually in the Orion Nebula, they found they can see these like little bright circles of material, and they think what's happening, or they're pretty sure what's happening, is inside here somewhere there's a newborn star. And all this dust has come together, and the star has just basically started to come to life, and the light has been spread out through all this dust, and it's lit these sort of conglomerations of dust and material. It's lit it up. So there's basically a brand new young star, might only be a few million years old, in the centre of these, possibly planets forming, or have formed, and it's slowly pushing all the remaining bits of dust away as the star starts to shine. Now, it was back in 1995, they actually found the first planet orbiting, the first normal planet orbiting a normal star. They found one before then, but it was orbiting a pulsar and it was a bit unusual, so they don't really count. The first one was 1995 in the constellation of Pegasus. We're orbiting a star called 51 Pegasi. It's about 50 light years away, and they've been able to measure the weight of it. And it weighs about half as much as Jupiter. It goes around the star once every 4 days. Right? We take 365 a quarter. So it goes around once every 4 days. And because it's in the constellation of Pegasus, a lot of people think they should call it Bellerophon, which is the name of the rider of the horse Pegasus. It's not an official name, but it's one that a lot of people think it should be called purely because it's in Pegasus. So it would be suitable. So if we go back to that image of Jupiter orbiting the Sun, and it was pulling the Sun, making it wobble. So you imagine if we were looking top on to a star and this big planet's going around, that star would be doing this little sort of circle in space. Except of course we wouldn't see the planet. We would just see this little star just doing little wiggly circles in space. But these little wiggles are extremely small. The only way to measure them, you have to measure the distances, the angular distance to many other stars to be able to calculate that this particular one has wobbled a tiny little bit. And from that, you can deduce the size of the planet and the weight of the planet and how far away it is, and of course the orbital period by how long it takes to do a wiggle. But as a result of how difficult it is to do, they've only found literally a handful of planets this way. This is not a good way to find planets, what they call exoplanets, which are planets orbiting other stars. If you imagine though that we're lucky enough, instead of looking down on the top, if it was orbiting and it was coming to and fro directly in our line, so the planet is going this way, some of them will be directly on because they're just randomly scattered. So we'll be lucky enough that some might be going around directly in front of us. So if we swing this around, this is what we would see. We would see the star actually getting closer and further away from us. Now if we take the light from a star, split it up into a spectrum, we find we get all these black lines. It's what they call the absorption spectra. And each of these little black lines correspond to particular elements like sodium and calcium and all that. And they're in a very precise location. We know exactly where they should be. So if we zoom in on one of these lines, right, we concentrate on just one of these lines. As that planet goes back and forth, we've all heard the Doppler effect. The Doppler effect, as the star gets further and closer to us, will make this thing move slightly back and forth. So we'll see as it comes closer, the line goes to one end, as it goes further away, it wobbles away. So we'll see this line actually move. The movement is very much exaggerated, but we would see this line move back and forth. Then we can simulate this. We have our star. We have an unusually large planet. That's only for convenience. And we have our little spectral line. If we change that to sound, so we have a very definite tone. Now that tone doesn't change. That's exactly the same tone while I do this. but you can hear the Doppler effect. So what we can hear with our ears is what we can see with the telescope. We'll see those lines wavering back and forth, back and forth. And with that, we can measure exactly. I'll keep spinning until you take a photo. Right. At the same time. So that wavering is only the Doppler effect. And you get the same effect with the star. It moves that particular absorption line back and forth. And we can measure that and we can calculate, we know exactly the period because we know how long it takes to go from one end to the other. So we can use that to determine that there's a planet by measuring those lines. Now another way of detecting planets, if we imagine we're just looking at a random scattering of stars. Some of them have planets, right? These ones have planets, these don't have planets. Just randomly, some of them will be looking top on, some will be looking slightly side on, some even more side on. Some of these will just happen to line up that, as seen from the Earth, the planet will go directly in front of the star at some time, just by pure random chance. These ones here, of course, we won't. The only way we could detect something like this would be if we could measure the star wobbling, which, as I said, is very, very difficult to do, because we won't get any of the other effects. But these ones here, we can see the planet would move directly in front of this at some time in its orbit. So if we take, this is actually a picture of Venus travelling in front of the Sun. Now as Venus goes in front of the Sun is slightly darker because it's got this little black dot. So a tiny little percentage of the Sun's surface has been blacked out by this planet. It doesn't matter how far away you are, that exact percentage of light has been wiped out. You could be 1,000 light years away. It will still dim. But of course, the further you are, you have to be more sensitive because it's dimmer. So you imagine this planet going past our star somewhere out in space. As the star goes in front, if we monitor the brightness of this star, because we won't see it, it's just a dot that has no sides. But the dot will get slightly dimmer. We're talking 1/10% or considerably less. So maybe even 1,000% dimmer. But if we can measure it accurately enough, we will see this planet literally go past, even though we can't see the planet. And this is a method that they're using on the Kepler telescope. You can see how big Kepler is. It's huge. And it's been out there for a couple of years already. And it's staring at a particular place near Cygnus, where there's lots and lots of stars, but it's just a little bit off to the side of the Milky Way. These are all the CCD detectors. It's actually measuring the brightness of about 150,000 stars every few hours. So it goes through, measures a few thousand stars, moves on, measures a few more thousand stars, and then comes back, starts all over again. Measures these brightnesses very, very accurately for 150,000 of them. Just looking for one of them going a little bit dimmer, and then a particular time later, it goes dim again while it's down. And then exactly the same time later, dim again. That would mean there's a planet which goes around exactly the same period every time, just like the Earth. Now it has some results out already. This is only a very small sampling. Some of these were released not long after it actually started. And you can see they can measure the approximate mass of the planet. They know the orbit, of course, very easily. And some of the stars, they know how far away they are. They can estimate the mass, so particularly they find a lot of big planets because big planets are easy to find because they make the stars wobble and put big black dots in front of them. So they're much, much easier to find. So we expect to find lots of big planets. At the moment, they think there's about 1,200 planets that they may have found. They've confirmed some of them, but at the moment it's about 1,200. And they think about 68 of them could be around about the size of the Earth. Just roughly. They won't know until they've done a lot more measurement.